The title of the talk is maybe a bit cryptic if you haven't come across these things. So reasoning with cancelings about Morse reductions, but don't worry. Even if you haven't heard about either of these things, at the end of the talk, you'll hopefully have an idea what these concepts are about. What wasn't part of the title was that, as was already said, I'm using Cubical Agda and Cubical type theory in these two projects that I'll talk about. And I guess, yeah, most of you have heard about homotopy type theory at this point. It's not all that hot anymore. It's 15 years old or something. And that's kind of a foundational program which tries to make sense of equality in intensional type theory, which was always something very mysterious, an analogy to paths and homotopies and topology. So kind of to make sense of an equality between two elements in the type by viewing it as a path, and then if you have maybe a higher equality, so kind of equality between equalities, to treat these as homotopies. And this correspondence kind of was a very fruitful thing to have to make sense of equality in intensional type theory. And cubical type theory can be seen as a sort of implementation of homotopy type theory. So cubical type theory really takes this correspondence very literally, and it takes some properties of topological spaces and makes them kind of principles of logic. So in this way, we can view cubical type theory as a sort of logic for homotopy types of topological spaces, because these types, these equality types, they really have kind of structure, higher structure, and what was originally a property of cubical sets, so this is a particular model of topological spaces, are now reasoning principles. And one such property is the cancelling property. So this was a property of cubical sets that Kant came up with to characterize which cubical sets characterize spaces, kind of. And now this is a reasoning principle. So this is kind of a crucial feature of cubical type theory. And what cubical type theory achieved as well is it kind of did all this addition to type theory without breaking its computational content, as it's often said, or it just means it's really a programming language. So like homotopy type theory in the beginning, there were just people trying to impose what they thought would be sensible in a very ad hoc way. So then there were some axioms like the invariance axiom you might have heard about, but these didn't compute. Like if you had a proof containing an invariance, this just got stuck. So this was not very satisfying. So cubical type theory rectifies this and really is a programming language, a total programming language. So you can't write anything that doesn't terminate, but for our purposes, that's more than good enough. Today, really, what I wanted to talk about is two things, two kind of sub-projects, which try to, which are about these two features in the following ways. So first of all, I want to make sense of this Kant-filling reasoning principle, because it's very tedious to come up with these Kant-fillings, especially when starting to formalize in Cubical Agda. So I was just trying to make sense of this and devise the tactic to kind of come up with a lot of these Kant-fillings in practice. So this is what the first half is. Then the second half is about a concrete formalization project, where we also will need these reasoning principles. But what we formalize is something from topological data analysis, or roughly speaking, computational topology. So computational topology, I guess, is a very natural area to be formalized in Cubical Agda because, well, we want to compute, which we can do in Cubical Agda, and we want to talk about topology, which we can do in Cubical Agda. So that's quite neat. What combined, or like what I think is common to both of these projects is, I really just try to use Cubical Agda and kind of make it more usable. So it's really like pragmatic considerations looking at this language, which kind of came out of a very foundational program. And there's a lot of debate on the foundational issues. What theorem prover should we use? What language should we use? Which logic? Which should we use? Higher order logic dependent type theory? Which kind of high dimensional type theory should we use? So can we just set aside all these issues? We just try to go with one particular candidate and then yeah, this will hopefully also shed some light, yeah, on what are good formations. Yeah, but it's really more a pragmatic point of view that I'll take in the following. So about the first half of the talk, we want to come up with a solver that derives the ominous Canfellings. So I said that in cubical type theory, we make sense of equalities and higher equalities by treating them as paths. So really, in topology, a path is a function from some product of the unit interval into your space. In this case, the space is just our type. So the cubes that give the cubical type theory its name are really these maps from the n-fold I into a type. And the setting that we consider is we will only look at paths of a single fixed type. So we have this kind of notion of a cell context, which allows us to prescribe all the kind of structure that a particular type has. So for instance, here we say, okay, we have in our type X and Y, which both have, well, it's just an empty bracket. This is called the boundary of this element of the type. So X and Y are just yeah, zero-dimensional cells because they don't have any variables in them, and hence we don't have to prescribe any boundaries. Really, these are just points X and Y. And then Q does depend on some variables. So it's kind of a function from I into our type, which means it's a one-dimensional path. So it's really a line. And we say, well, at the one endpoint of I, so I equals 0, we'll be mapping our things to X. And on the right endpoint, I equals 1, we'll map our path to Y. So kind of really this syntactic description just says, if we have a path from X to Y, and this is called Q. So this is kind of the setting that we consider. And in this way, we can talk about this homotopical structure that is contained in, or like that this type possesses. Then we can wonder about, well, what kind of new paths can we build? For instance, just using our initial 3 elements, we can say, well, in this cell context describing our path, suppose we have another interval variable I, we could again just say, well, we have an element X, which now lives in kind of a one-dimensional context. So this is really now considered a path. And the boundary of this, because it's just the blob X, will be on both sides constantly X. So in this way, this kind of X considered in the interval context I is now a one-dimensional path, which goes from the zero-dimensional X to the zero-dimensional X. So this allows us to kind of build new terms with these boundaries. And what we say in the following is that kind of if we didn't know about the X in the first place, this would be a boundary problem, right? We are faced with some boundary, we have to produce something of this boundary. And now we found out, well, actually it has a simple solution, this boundary problem. Maybe kind of the constant X path has exactly this boundary that we're looking for. Yeah, and in this way, we've shown already that our notion of equality, right? We still wanted to be behaving something like equality is reflexive. Everything is equal to itself because you can do this construction for any zero-dimensional cell. So this already works. So this is, of course, not super helpful yet. We need some more power to build more interesting cells and to solve more interesting boundary problems. For instance, we now want to show that we can invert paths, right? So we have our Q going from X to Y. We expect that we can also go from Y to X in some way. So the boundary problem says, okay, we need to produce something which has boundary I equals 0 Y and I equals 1 X. And to produce such a term, we'll now use the Canfellings. And what Canfelling says is, if you are looking for some cell, but you don't really know how to build it directly, we can build it by constructing a higher dimensional cube, so a 2-dimensional cube now, where all the sides are filled in and matching together in some way, and then the Canfeller of this open square will be the missing side. So here Q goes from X to Y. So this means we have here an X endpoint, and we can just put the constant X paths on these two sides. So this fits together. And then cubical type theory says that, well, the filler of this thing, there's also some syntactic representation of these open cubes, but the filler of this thing really solves the boundary problem. So this is the search problem that we are concerned with when using Kant fillers to solve boundary problems in cubical type theory. So if you've used cubical Agda at some point, maybe you will have come across like these boundary constraints, and yeah, these are the kinds of constructions you need to carry out to resolve these.
There's an axiom that says that you can always find such.
So this is really like a primitive term in the logic, if you will. And kind of there's a normal form of these things, so they compute. But this is kind of really some additional thing that cubical type theory adds. In cubical Agda, they're usually called HComp. So you might have come across them as HComp, because sometimes it's Kant filling, sometimes Kant composition. Yeah, but the crucial thing is you kind of have something that you need to fill, and you can fill this by looking at something higher dimensional, which has the missing thing or which has the thing you're looking for on the missing side. So let's try to do this more systematically, this fitting together things in open cubes. At the top now, we have a cell context which says that we do not only have a path Q from X to Y, but also we have a path R from Y to Z. And we also expect to be able to compose them, right? Or if we just look at this as equality, we expect that our equality is transitive. So we want to find something which goes from X to Z. What we just did on the previous slide was, well, we can't construct this directly, so we'll use Kant filling, where we have three missing sides that we in some way need to find. So let's introduce some variables. These variables have domains. So for instance, here, the only thing that fits in here is the constant X path, right? For the other side, we have a bit of choice, because both the constant Z path and the R path will have Z on its right endpoint. For this side, we don't know at all what's going to be put in there. So this could be any of the cells of the cell context. And then we also said they need to be fitting together, right? So this is what these constraints say. So just the left endpoint of the left side and the left endpoint of the bottom side need to match. And now, if you did some computer science, you might have come across these things as constraint satisfaction problems. So really kind of phrasing this problem in this way means we've already solved this, because there are finite domain constraint satisfaction solvers, where you can just plug in a bunch of variables, a bunch with domains and a bunch of constraints on these variables, and then they'll do some backtracking, for instance, to solve this. So really kind of to resolve these automatically, all we need is these P's, and then this will be carried out quickly. There's one caveat though, because this only works if we can directly solve all the sites, but it might be that some of the sites are themselves the result of Kant fillers, right? So we have this infinitely expanding search space. So unfortunately, our problem is not decidable. But the second insight that we can use is, well, if we can't solve like this three-way path composition, so now we have another path P, which goes from W to X. And let's suppose we want to compose these three paths, P, Q, and R, to go from W to Z in one step. We won't be able to solve this directly, so there's no way to fit these three paths in here that makes it work. What we'll do instead is we'll try to fit in as many of the sides as possible. And then whatever is left, we treat as a separate boundary problem. So we just say, okay, we can solve this question mark here as the filler of this guy, supposing that we can solve this boundary problem going from W to Y, which we've already seen just works by composing the two domain paths. So in this way, if you have the filler being put in here, then this is really a solution to the boundary problem. So the second insight that we have is, to
manage the search space, just try to solve separate CSPs. If this doesn't work, leave some sites open, solve the call the solver recursively, and in this way, yeah, kind of do some sensible exploration of the search space. So this works already, yeah, relatively immediately, and I guess it's also possible to solve these by hand, these problems. Now, as an example for something more intricate, we've now composed these three paths by essentially first composing P with Q, right? So P is now on here, and then with R. But you can also imagine that you compose these three paths differently, where you have now the counselor on the right hand side. Right? So we go first along P, and then we compose Q and R on this side, and then this will in some way be P composed with brackets Q composed R, right? So kind of if we call these compositions this, then we might wonder, well, does it matter in which way we compose? And it should not matter. And indeed, we can show that it doesn't matter by establishing inequality between these two paths, right? So now we want to say, well, it doesn't matter if I compose this way or this way, and it doesn't matter because I can find a cell which witnesses this. So having the constant W path and the constant Z path on the other sides of the square, this is now a higher equality that we need to resolve. And to resolve the square, we will have to construct a counselor of an open three-dimensional cube, right? One dimension up. And you can already see where this is going. This is going to be relatively tricky to do by hand, not impossible, but tricky, which is why we can happily use this solver. So the things that I mentioned to you, the constraint satisfaction solvers and this kind of gradual expansion of the search space, we've implemented in a solver which can resolve this composition problem automatically with a beautiful looking term. So this is already in Cubical Agda syntax. So we are able to just copy this. I managed to just make this smaller. Didn't quite manage to copy everything. Let's put this in front. Now this is, here we see this associativity proof goal, right? So we have here, yeah, you can't quite see this. This is our proof goal. Actually, if you ask Cubical Agda to normalize a bit differently, then you see that this is really what we've just had as well. Like HCOP is the Cubical Agda term for fill, and these are the different ways in which you can plug these three paths on the missing sites. So this is what it looks like in Cubical Agda. And now, yeah, I was actually to refine this. So really, this proof term solves our problem. So of course, not a very beautiful proof term, but it does the trick. And yeah, some of the things you can actually leave out, like these H fills, they are kind of inferred by Cubical Agda. Yeah, but in this way, we can quickly resolve these things. We can also inspect kind of what kind of search our solver did. So it actually had to do some amount of backtracking. So going through this, you can see how it kind of builds these open three-dimensional cubes and tries different configurations. Yeah, but these combinatorial problems, computers are good at, and we are not necessarily. So this works quickly in a few milliseconds. So yeah, you can try this out if you like to. We also are currently really making this part of Cubical Agda so that such that you only have to call this from Cubical Agda. Also, the solver has some extension. So there are some kind of admissible constructions on cubes which are even simpler than Kahn fillings, involving interval substitutions. So they're also taken into account. In essence, they kind of give you just a bunch of constructions that you otherwise would have to do on and on and on with Kahn fillers directly. Yeah, so this works quite well for these lower dimensional examples, also for some higher dimensional examples. So if you've come across the Ekman-Hilton argument saying that composition of two-dimensional loops is is commutative, kind of the cubical version of this, we can also resolve automatically. So kind of some non-trivial results we can solve. So kind of, yeah, as a quick recap of this first half, we can, yeah, say that with some fairly basic algorithmic techniques, we can already resolve kind of this fiddly looking at, yeah, not very easy reasoning principle in the beginning. Then, yeah, this is really independent of the concrete flavor of cubical type theory. There's also RedTT, which implements Cartesian cubical type theory, so it also works for this. And pretty much all the type theories, cubical type theories considered at the moment. Yeah, and it gives us kind of a practical approach to these boundary problems, which in general are quite tricky and undecidable. So this is kind of all we can hope for now. Any questions so far about this business? Maybe this gives you some starting point if you dare to formalize something in Cubical Agda. Yeah, but these boundary constraints, I think this is really what makes Cubical Agda annoying to use in the beginning. And actually, yeah, it's just some combinatorial problem that we can resolve automatically. That's maybe the bottom line. Yes.
Can I go back to, on an earlier slide when you were showing P composed with Q gives you the same thing as Q composed with P or something like that. Maybe back one slide before that. One more. Yeah, you have on the left-hand side, you have a constant X.
Yeah.
Couldn't you have put Q on the left-hand side and R on the bottom and constant Z on the right? That is, it seems like your domain for your variables should include the other possible ways of composing Q and R.
So Q goes, maybe it's not entirely clear from the diagram, but we only go from bottom to top. So we have to have something which on kind of the end point, the right end point of our path has an X, and Q has a Y on the right end point. I think it would have been maybe helpful if I had put also the vertices in there, but Q crucially ends at Y, and we need to have something which ends at X.
Right. What I meant was Q inverse. So.
Yeah. So this is this is a good point. So this inverse, this is what I mentioned with these admissible rules. So there are kind of additional things you can put into your cubical type theory to carry out constructions that you have to do quite often. And taking the inverse is such a construction. So Cubical Agda, for instance, has this involution operation on the interval variables. And you're absolutely right. So Q inverse, we would be able to put in there. However, not all the cubical type theories have Q inverse. So for instance, RedTT doesn't have this, which is kind of the search tactic works independently of what more basic transformations you can do on cubes. So kind of these contortions, these can be the involution operation. So this allows you to primitively kind of invert a path. And also these wedge and V constructors you might have seen allow you to kind of stretch a path into another shape more primitively. And then it goes quicker to resolve these proof goals. But kind of they are only thought to be admissible. Like we still need this canceling operator and the inversion operator doesn't need to add something in terms of expressivity to our logic.
Okay, thanks.
Right, thanks for the question. Any other questions at this point? Then we can go to the second half, which is now a formalization project using Cubical Agda. And in the end, we'll also return to these cancelings to see how we can use these in our formalization. So the formalization project that I was looking at is in the field of topological data analysis. So some research on TTA might have given you this selling slide already. I'll try my best to also sell this well. So the idea of topological data analysis is that we can in some way use the tools of algebraic topology to make sense of data points, or like to give meaning to data sets. So for instance, here, if we have some data points, which are just some points in some metric space, and they kind of seem to form something like a circle, we want to be able to somehow capture this with algebraic topology, because that's what it's all about in algebraic topology, right? It's about holes and circles and all that. And TDA allows us to do this. So TDA says that, okay, if you have some data set, associate a topological space with this in some way that we can then study. So one common space to associate is the Vietoris-Rips complex, which in essence just says whenever you have a few points lying close together, introduce some simplex into your space, to your simplicial complex, and then we can study this, right? And here you would already be able to see, okay, this seems to form a circle. Before we compute any invariance, what usually happens is that the size of this complex needs to be reduced, because it will be quite expensive to compute the invariance of this space, which isn't necessary really, because a lot of the simplices are superfluous in this complex. So discrete Morse theory is kind of the central method of TDA, which gives us a principled way of reducing the very large simplicial complex potentially into something which really gets at the core of the topological features that we're interested in. So for instance, here we would maybe be able to collapse all the cells apart from a one-dimensional and a zero-dimensional cell, and hence this really captures the topological features of this Vietoris-Rips complex, and we can then very cheaply compute, for instance, the first homology group to see that what we were given in the beginning was really forming a circle in some way. So this is now being used already, this pipeline, so you can do all sorts of kind of cool image analysis with TDA. There's one refinement of this pipeline, persistence homology. That's likely something that a TDA researcher would also have told you about. Unfortunately, I won't go into this because we haven't really incorporated this yet into the formalization, but this is another crucial method. Well, discrete Morse theory, persistent homology are the two central methods of TDA. We will only talk about discrete Morse theory today. But kind of the long-term goal, so the formalization is with an eye on at some point being able to do this complete pipeline in Cubical Agda, because then, you could put in a data set and get some properties out of this data set. And this should happen then in a way that every step of this pipeline is verified. So that's kind of the motivation for this. But for now, it's really only about the second step in this pipeline, the discrete Morse theory. So I said that discrete Morse theory kind of reduces a complex with a lot of cells, which are not really relevant to us, to the core, like the critical cells, they're usually called. And it does this by, taking essentially like a recipe for collapsing all the cells, and then giving you what comes out of it after collapsing everything. And then it also tells you, really, you're allowed to just look at the smaller ones containing only the critical cells, because really the smaller complex, the Morse complex M, they are equivalent as far as we are concerned. So that's kind of roughly the idea of discrete Morse theory. So this works, of course, in general for some, usually a simplicial complex you would put in, get a cell complex out. Unfortunately, I haven't been able to talk in such generality yet. So sorry, this is just the example from the slide before, right? So if we had a matching, which is comprised of everything apart from two cells, then the Morse theorem would say, okay, really these two cells, they make up a complex which is really the same as far as we are concerned as the original complex. And kind of classically, or like, the original work on discrete Morse theory from 25 years ago was only on the level of homology groups, because I guess this was the way we were talking about equivalence of spaces at this point. More recently, kind of there's other work which, yeah, in other settings carries out discrete Morse theory up to a final notion of equality, namely homotopy equivalence, which suggests itself as inspiration for our formalization project, because we also want to formalize this Morse theorem up to homotopy equivalence, which is just equality in Cubical Agda. So the formalization project that I carried out so far, I said, doesn't work for very general spaces, and namely it only works for one-dimensional simplicial complexes, which are graphs. And the result that I formalized says that if you have given some graph and some acyclic partial matching, so we'll say that what this is in a bit, then we can characterize the Morse complex in some way. And then if we look at these, both the graph and the Morse complex as kind of homotopy types, so kind of we take this combinatorial description of the graph and we embed it into Cubical Agda to kind of be able to talk about the homotopical structure of G, and we do the same for the Morse complex, then we can really establish that these are the same things as far as Cubical Agda is concerned. So kind of these 3 steps we have to carry out to formalize Morse theory for graphs. So the first steps is to say what basically partial matchings on a graph are. And they have a relatively nice and direct characterization. So a partial matching is kind of picking out a collection of the cells, and it does this by mapping always a vertex and an incident edge to one another. So we kind of have a big graph, and then it just picks out pairs of edges with incident vertices. And this is acyclic if we can't go along such matched pairs in circles, i.e. if at some point we end up somewhere which isn't matched. So if you look at the example here on the bottom left, we have a small graph containing only 4 edges and vertices. Then a matching would say, okay, I match V to VU, and this vertex to this edge, and this vertex to this edge. And it's acyclic because, well, even if I follow along this sequence of matched pairs, I end up at U, and I can't go in a circle. And this is kind of capturing that, we can remove these things that are matched without changing the topology of our graph, because if there was a circle and we removed that, then we would have really changed something about the topology. And so this is kind of the intuition. And then after characterizing these acyclic partial matchings, we can also characterize the Morse complex fairly directly. So this M0 are the 0 cells of our complex, M1 are the 1 cells of our complex. And really the 0 cells are just the vertices we didn't match, so that are not part of mu. And the 1 cells are all those edges that we didn't match. And we also have to say how they are connected to some critical cells in the graph. So I think again, an example makes this a bit more intuitive. So here in our graph, we matched everything apart from this line here and the U, right? So we expect that our Morse complex has 2 cells, namely something corresponding to U and then something corresponding to this edge here. And this is really what we have. Like we have only this U as a 0 cell, and then we have a line which is induced by this unmatched edge XU, and it's connected to U by going along this path, and so this is this path, and by staying constantly at U on the other side. So in this way, kind of it looks like it's a bit annoying, but this is really only the combinatorial data which says we have a single loop around our U. So in this way, we reduced our graph to this smaller thing. And now to the second step, because now we want to say that these 2 things are equal. And for this, we need to somehow make use of Cubical Agda. And we do this with the following higher inductive type. So higher inductive type just is an inductive type, which allows you to also state kind of higher path constructors. So to introduce homotopical structure into your type. And what this here is, it takes something which is graph-like. We don't even have to have as many properties as a graph has. We just need to have a base type 0, 0, and then a relation between C0 in itself. And given this combinatorial information, we'll just have 0 cells induced by the 0 cells of our relation, and then paths are induced by all the paths or the 1 cells in our relation. So for instance, with our Morse complex from before, we really would only have a single 0 cell and a single 1 cell, which is a path from the single 0 cell to itself. And this is, yeah, just the circle directly as it's defined in Cubical Agda. So we can just prove directly that really this Morse complex here is the same thing as the circle by pattern matching directly. But of course, the general result that we want to obtain is for some general graph, its Morse reduct will have to be the same thing as far as Cubical Agda is concerned. And to establish this result, we can give an equivalence between types. I should maybe take a break. Any questions so far? Like, does that make sense somewhat? Or have I lost you so far?
Not quite understanding the higher inductive type definition. Is in, I don't understand what the syntax.
Yeah, that's a good point. So we are constructing, this is direct Agda syntax. So data type, inductive data type, which has 2 constructors. So the first constructor says that anything in C0, we will also just have in C1. So kind of in the topological realization or geometric realization, if you will. And then whenever we have something which goes from X to Y and is contained in C1, then the X and Y will have a path between them. So what this means is we kind of, a graph is just a combinatorial gadget, right? And now we embed this into our type theory. So we have a proper type with homotopical structure, and we can use the reasoning principles of Cubical Agda to reason about these paths. So then we have the whole cancelling shebang to reason about these paths here. Because this is just for one-dimensional cells, this is also a known higher inductive type, which is, I think, just called a type quotient sometimes. You could imagine that if you had maybe a 2-dimensional cubical complex, so if you had like a 2-dimensional cell as well, then what you would have is a third constructor, which then says, given some 4-dimensional cell, introduce a square between the 4 lines that you say are related by a square. So that's the idea behind this hit. So I said to prove this now, to establish this equality, we want to establish a equivalence between these 2 types. And equivalences we define by just giving maps back and forth, and then showing that, well, it doesn't matter if we go along the first and the second one, we'll end up with something which is equal to the original bit. So for instance, for the first part, to establish these maps back and forth, we would need to come up with a map which goes from the lines in our Morse complex to the original edges of our graph. So we could do this by saying, okay, the line in our Morse complex is given by this critical edge between the 2 critical vertices C and D, which are connected to this edge via these 2 paths. So the gamma delta are kind of the sequences of matched pairs. And then we can embed this into the realization of our graph again by saying, okay, this edge here, this certainly exists in our graph. But then we would also need to go along the realizations of these paths, which kind of tell you, you can just concatenate the edges in your graph on the left side with gamma, on the right hand side with delta, to end up with something which goes from C to D. Maybe an example here would have been good to make sense of this. But yeah, the idea is we establish these maps back and forth, and then we have to show that, for instance, if we go from E to the Morse complex back to E, we have something which is equal to the original thing. So if we have this edge QV in our geometric realization of the graph, and then we go in the Morse complex and then back, then we'll have something which looks like this, which is the gradient paths that were reduced by the fact that QV was critical in this case. And we now have to show that these are equal, i.e. we have to construct a square between these two paths. The other sides of the square are given by some other constructions in our proof. And now to resolve such a proof goal, we can actually just call our solver, because if you abstract away from this and just introduce variables p, q, and r for these paths. So now we also have inverses directly, let's say, in our language, then really this is just a combinatorial problem, right? And on this you can call our solver, so you don't actually have to do any work to resolve this proof goal, because this is just combinatorial stuff with our machinery of Cubical Agda. And when doing this, we'll resolve this proof goal. So in some way, I mean, it's only formalized for relatively simple spaces so far, but I guess the benefit of working in Cubical Agda is once we understand this logic and language well, kind of you have tools to carry out such formalizations with less pain, let's say. Now, what this result allows us to do is to establish properties of essentially all kinds of graphs. So for instance, the example graph that we said was just equal to the circle. So for instance, in the Cubical Agda library, we have certain results about the circle, maybe it's homology group. So because this is equality by univalence, so I could have mentioned we establish this equivalence, and then univalence lifts this equivalence to equality. And then any property that holds of this thing should also holds of anything that is equal to this. So we can directly establish the homology of this graph. We can also, for instance, reason about infinite graphs. So just this long chain graph, we can collapse into a single point. So then we can establish that this infinite graph is contractible. So with this one Morse theorem, you kind of have a recipe to reason about graphs. You just have to establish a matching on this graph, which kind of tells you what are the relevant bits about your graph, and then you can treat this topologically and reason about this topologically. So this is kind of what we can do so far. Of course, it would be nice to reason about spaces that are of interest to actual people. And turns out that already going one dimension up would lead to something which is of interest. So if we can do discrete Morse theory for two-dimensional cubical complexes, which is something I'm working on at the moment, then we can, for instance, reason about images. So this pi, this is just a JPEG. There's a nice paper from 2010, which tells you how to turn this image into a two-dimensional cubical complex. And then once kind of we have formalized discrete Morse theory for two-dimensional complexes, we can reason about images and say something like, okay, this image really, if we go along the pipeline, then we can establish topological properties of these images. So this is, I think, the natural next step for this project. Of course, then we also need to formalize other parts of the pipeline. So for now, we just assume these matchings to be given, but there are also algorithms to generate them, which you would also need, because a user wouldn't supply the matching usually. So you also need to come up with good matchings. And then you also need to think about, well, what properties do I actually compute of these complexes when reduced. So there's already work using kind of traditional ways of computing invariance using a bunch of linear algebra. So this is this paper from 2013. But in the hot world, there are also kind of more recent approaches to invariance. So these synthetic cohomology theories, they might also be nice to compute, and they've been already developed in Cubical Agda. So it'd be natural to see if we can in some way use this. And then hopefully once kind of a basic pipeline works for some images, let's say, there are numerous other methods of TDA that I think would be interesting to look at and see if we can incorporate this. So let me close perhaps with just a very quick summary and some outlook. So as an own learning experience, like Cubical Agda was quite a mouthful in the beginning. So a good part of my PhD, I was just learning it. But it is quite powerful if you actually can use it at some point. So that is really quite nice, because I mean, talking about homotopy types usually requires a lot of theory, right? You need to work with some concrete model. And if you commit yourself to cubical sets, this particular model, then Cubical Agda really is a theorem prover with building cubical sets, right? So you get feedback on the correctness of your proofs. So this has been really nice. And it's really a programming language. It hasn't been used all that much. You might have heard about the flagship results that we couldn't compute 2 in Cubical Agda, which is a super nice result. But I mean, it's not really what people think of when they think of as computation, right? And would be cool maybe to use Cubical Agda properly as a programming language. And kind of course, Cubical Agda is not geared towards performance at all. But I guess the main takeaway would be, or like the approach would be, we do all the formalizations, know that it's correct, and then we can forget about the proofs and just compute with the programs. And Agda does compile down to Haskell. So in principle, we can get something out which also does work on real data sets. So I think this is reasonably feasible. In some version, this tool hopefully exists in the medium-term future. I think what would also maybe be a benefit of such a project would be that it helps to bridge a bit the gap between more abstract and more applied areas of topology. I mean, I'm myself not a topologist, so just as an outsider, it appears to me that people working with topological methods have vastly different methods. So just for instance, applied topologists care about simplicial complexes, more abstract ones usually about simplicial sets, and there's kind of very distinct methods in these two fields. And maybe having a theorem prover which takes into account some more abstract ideas, but also gives you a very concrete thing to play with and compute with, we maybe have something which bridges this gap a bit. And lastly, I think Cubical Agda, nobody expects it to be kind of the best tool to reason about high dimensional types. So there are simplicial approaches. There are other approaches based on globular theories of topological spaces. Whatever kind of we will converge to, or whatever turns out to be the best, I think we'll have shadows of these Kahn fillings and things like this also in like a theorem prover in 20 years time. So just working with it and using it, I think will already give us some insight what it's actually like to reason in such a high dimensional type theory, because it's a fairly new thing to have something like this laying around. And perhaps these practical experiences can shed some light actually what we want to develop in the first place. That's it from me now. Thanks for your attention.
Do we have any questions? Perhaps also online.
So if I understand correctly, so when you're constructing the Morse complex, the user needs to figure out a matching of the original. Okay. And after you construct the Morse complex, the user also needs to identify that the Morse complex that you get is actually the same as like a familiar object, like circle something you need to plug this space and like introduce it.
Very well spotted. So this is actually, I mean, when I say you get a lot of results for free, you're absolutely right. So we still have to like say, okay, actually what we talk about is a circle.
Okay.
But kind of yeah, I think this is perhaps something, yeah. Yeah, no, that's exactly the set pain point when trying to think about how to compute actual invariance of these spaces.
Okay.
Yeah, I'm not quite sure how we connect this to computing invariance. So for now, there's manual work involved in these steps. Yeah, absolutely right.
Can you maybe give a more concrete idea of what people use topological data analysis for? Is it more like I have some data and now I know the homology group, this is cool, or
so I'm trying to give the best sales pitch I can, but I think there are various applications now. So for instance, in cancer detection, like if you have an image of like some tissue, then you can characterize certain subtypes of cancer with TDA. So there's a paper I read at some point where they do exactly this. So if you then, I mean, you also have higher dimensional holes and then all that. So you do have quite a lot of structure, or you give quite nuanced meaning to images. And yeah, this is apparently useful. Yeah.
Is it that maybe in the future we'll also like to connect it to the persistent homology? Do you have any idea how that works, or because
yeah, so yeah, so persistent homology is actually something where there has already been quite a lot of formalization work. So in COC from 10 years ago. So yeah, I have the feeling that it's actually that's not necessarily where like Cubical Agda will be all that relevant. I mean, so persistent homology, the idea is that you, when we in the beginning took this data set into a complex, just arbitrarily said that, well, for a fixed distance, we'll introduce a simplex of like points like close together, but you don't know this distance in advance. So persistent homology says if you take kind of a range of these distance parameters, you get a filtered complex out, kind of something which has ever more simplices. And then the homology groups that are most persistent across the range of distance parameters are the most relevant ones. I have the feeling, yeah, it's just formalization work to do this, but I don't see any fundamental obstacles to that. Yeah, but I haven't thought about this too much.
Because I guess it naturally introduces like real numbers into the picture, no?
Yeah.
Distance. Real numbers are hard.
Yeah, I guess we would have to have some discretization of this process in some way. Yeah, I'm sure these guys have thought about this more than I have. Yeah.
So when establishing these equivalences, which involves a lot of manual work at this point, is there any automation of that at the horizon?
So I should say, so I mean, so this is the this equivalence we have once and for all, right? So we have for all graphs that they're equal to the Morse reduct. Then the question is like, how do you know that the Morse reduct is equal to this?
Yes.
And yeah, you spotted that you just have to recognize this, and then it's just pattern matching to establish that they're equal. So there will be easily a tactic divisible for that.
Okay.
But because metaprogramming in Agda is a pain, I haven't programmed this yet. Yeah, but so kind of once you spotted, okay, my Morse complex is actually this type, then it's just pattern matching to establish this.
And if the original graph is finite, like does Agda support like writing some kind of a meta program to automatically like find a suitable matching and then like prove that it's correct and then use that for the first step automatically? Or like does a human need to sort of like carefully come up with a matching that like makes the end result like as nice as possible?
Yeah, at the moment I still have to come up with a matching.
Yeah.
Yeah, but I think yeah, you wouldn't even have to do Agda metaprogramming, right? It would be just kind of formalizing an algorithm that comes up with matchings. So there are a bunch of algorithms out there. In general, it's like a hard problem because that's why there are a lot of heuristics. Yeah, so you would just have a program, and then Agda would maybe say, yeah, you always spit out a correct acyclic partial matching, right? This would be kind of the correctness criterion that you need to formalize. And then you could use any such matching in your proof.
Right.
So this is kind of more formalization of the pipeline work. So yeah, in principle, there shouldn't be all that much hacking and metaprogramming
Mhm.
involved.
Right.
Yeah. Yeah, but I think the last step where we take some Morse complex and compute invariance from it, there has been the most work already within like a classical setting, and that's the part that I haven't thought least about in the cubical setting, how to do it best.